Example 2 of the disk method. With example 2, you'll quickly note I started with the same function as example 1. However, in this example I'm asking to revolve about the y-axis, and notice my boundaries. They're no longer in terms of x, they're in terms of y. Now I have the same picture drawn, but this is going to be a completely different volume. Why? If I'm going to revolve this about the y-axis, put my arrow there saying revolving about the y-axis, I need everything in terms of y. So this function right here that says y equals rad x plus 5, I can't use that. I'm going to have to solve this for x. And so that'll have to be my very first step. I'll say y equals radical x plus 5. I'll bring the 5 over. Y minus 5 is equal to rad x. I'll go ahead and square both sides. So this becomes y minus 5 squared is equal to x. Now, as I look at that, I'm being given these boundaries saying to start at 5 and end at 7. They want me to revolve this. And if I revolve this, my axis of revolution is the y-axis. It tells me that I'm going to have to measure from the center out. And it's going to create this three-dimensional object, which would be kind of like a tornado shape. It's going to be this cone that has curvature to it. That's what they want me to find the volume of. So using this information, I can say that my volume would equal the integral from y equals 5 to y equals 7. I'm going to leave the pi in there for this example. And as I look at this, and I'm looking at my radius, the radius would take the shape of this thing here. So this would be y minus 5 squared. Y minus 5 squared. But if you recall in our last problem, we're looking at this formula that says that we have to do pi r squared h, which is pi, could be f of x, g of x, doesn't really matter what it is, g of y, squared. I have to square something that's already been squared. My function is telling me I'm squared. So when I square a square, I'm going to raise this to the 4th power. And then I'm going to have a dy there. Now, that may get a little bit confusing because when you look at this, you're going to be like, well, doesn't that mean 4th dimension? It's not really a 4th dimension because this curve here that you see, this black curve, is defined by something that's already been squared. It's simply a parabola that's been kicked over on its side, and I'm only worried about this distance from 5 to 7. This is defined as my function. So whatever that function is, that's why I keep going back to this paper here, whatever the function is then being squared. That function, as it's being drawn on the paper, is only one dimension. It's only, or 2 dimensions there. And then when I square it, that's giving me the piece that I need. So it's saying that I'm taking this as one dimension, because the radius from here to there, it's one direction, one dimension. I square it, and then I do my dy. So it's pi r squared. Remember, this is nothing more than disks that are being stacked. So it's here's a disk, here's a disk, here's a disk. And these disks, when we talk about the width, they're infinitesimally small. So as you drop this down as your axis of revolution, this was one dimension, that's my radius, squared takes me like this circular with the pi, so it's pi r squared, and then the height gives me my 3rd dimension, if that makes any sense. So whatever your function is, you have to square it. In this case, it's raised to the 4th. Now, once again, I'm going to cheat. I'm going to put this in my calculator because I'm more interested that you guys are making the transition between what's going on in your calculator and what you're doing physically on paper. So physically on paper, I'm turning this into a 3-dimensional object. But on my calculator, first off, I can't even put a y in this calculator. It has to go in as an x. So I'm going to call that pi parenthesis x minus 5 raised to the 4th, and then I graph it. Oop, hit the wrong button there. Now as I graph it, this graph is actually a representation of my volume, and I want to go from 5 to 7. So I do second calc, option 7. I start at 5, I end at 7. It's given me an answer here that is represented as an area, but that area is actually a volume. So when I write this formula here and then I go to my answer, it already has the pi in it. So I'll say that this is 20.106 units cubed. So I let that calculator do all the work. What you have to walk away with today is understanding that every problem that you do, you have to set up as a volume equals an integral. Now it could be x, it could be y, it depends on the axis of revolution. I'm going to go x equal a to x equal b. You're going to have a pi as a scalar that's in there. And then you have to take a function, that f of x or g of y or whatever the case is, and you square it. And that f of x is always going to be, if I'm doing an x value like this, it doesn't matter what the curve looks like, but that's going to be your distance from the curve to your x-axis. That's one dimension that gets squared, and then you do your dx in this case. So that's your pi r squared h. dx is your h, it's being stacked this way. R squared is what you're figuring out to be the distance from your function to the x-axis, and the pi is just part of a scalar. So this part is what gets translated into your volume, and then you integrate it. There's your second example of how to use the disk method for solids of revolution.